Okay, now let's talk about the last section of this futures chapter. So, the last section is about commodity futures pricing. Um, this or the pricing of commodity can be borrowed from the pricing of equity index futures. Remember that in that section we talked about spot futures parity theorem, right? Um, so let's first recall this spot futures parity theorem in the case of stock futures. We learned F0 equals P0 plus P0 times RF and plus D, which is the dividend. So to understand this formula, we discussed we could use the cost of carry model, right? So basically, there are two ways to get your equity investment. You can buy it today, and if you do this, you will have to pay some cost. Here it's your interest cost. However, this cost will be offset by dividend, because if you hold stock, you will get dividend. And then the second way to get your equity investment is to just enter into the long position of a futures contract. And on the maturity day, you will pay F0. Then you will get your investment. And we said these two methods should give you the same result. So based on this, we say F0 should be equal to P0 plus P0 RF minus D. And then in the case of commodity futures, the idea here is the same. We could again use this cost of carry model to think how should we price commodity futures. So let's say F0 here is the futures price and P0 is the spot price. To be more accurate, it's today's spot price. So it's the current spot price. Current. And let's assume C is the carrying cost. And then you can see that again, using the cost of carry model, we could get the same idea. Right? So you can see that we don't have dividend here. But compared with the parity theorem on equity index futures, we have this additional C here. So what is this C? Well, because we're talking about commodities. So compared with equity, we have some additional cost, right? For example, we could have storage cost, right? So if you buy wheat, then you have to store wheat in a storage unit, and possibly you have to pay some fee to that storage unit. Right? And then we also have this we also have this spoilage. It basically means that if you store wheat for like maybe 3 months, maybe 0.5% will just expire. You cannot sell this wheat anymore. So this is called spoilage. So taking these costs into this formula, that's why we have this C here. Essentially, it says, hey, if you buy your wheat today, you have to pay this interest cost and you have to pay this additional carrying cost. And then you can see that after getting this formula, of course, we could write this lower letter C equals capital C divided by price. So we will get the same formula, just in a slightly different form. Okay, a second way to think about the pricing formula is to use in the hedging portfolio. So let's say now you have a long let's say now you have a long position in this commodity. So if you want to hedge against future price movement, then you should take a short position in the futures. Right? So that's the basic idea of hedging. Now let's see how this works. So here, obviously you will take a short position in futures, and then you will have a long position in this commodity. Here we assuming you're borrowing money to buy this commodity. So you would borrow P0 because P0 is today's commodity price. Right? And then we assume there is this interest rate, RF. And let's see what is your cash flows at different time. So let's say we first look at your today's cash flow. So if you enter your short futures position, then there's zero cash flow because again, it's a futures position. It's costless to enter into futures contract. And then you borrow P0, right? So you will get cash inflow of P0. And then you will use this P0 to buy this commodity. So you will have this P0 cash outflow. Now, what is the cash flow at time t? So on this maturity date, your commodity will be worth PT. Right? So this is essentially the market price of this commodity on the maturity date. But you have suffered because of the carrying cost. So you have to pay this C, which is the carrying cost. And then at time t, you have to pay back your debt when you borrowed P0. So the cash outflow would be P0 times 1 plus interest rate. Right? And then you have a short futures position. And we know that if you take a short position in futures, then your profit is given by the initial futures price minus the spot price on the maturity date. Right? So this is your profit. And combining all three cash flows, so you will get the final cash flow on the maturity date. And because when you established your position, you paid nothing. So this guy has to be 0, right? So this essentially means F0 equals P0 plus P0 RF plus C. The idea here is really similar to how to price the equity index futures. Right? So it's just like a very small modification of the formula of the methodology we learned in the section on equity index futures. Now, a caveat about this commodity futures pricing is this nice simple spot futures parity theorem is only useful when this commodity can actually be stored. Right? So this is the key here. Well, you might wonder, are there any commodities which cannot be stored? Well, there are some. Right? Think about electricity, right? At least conventionally, you cannot store electricity in large amount, right? Of course, because of technological advancement, this could be possible in the future. And then some commodities will not be stored because of economic reasons, such as agricultural commodity. Right? The reason is because agricultural prices come in cycles. For each harvest cycle, it will actually decrease. So if you look at this picture here, what you can see here is we have 3 cycles here. So for the first harvest, right, you can see that price would actually go up. But then the more important feature is after the first harvest, price will drop. And then for the second cycle, you will observe the same pattern here. For the third cycle, same pattern. So this basically implies that if you wanted to buy, let's say this is wheat, right? Or canola, right? Let's say this is canola. Let's say if you wanted to buy canola, then you will, let's say you want to buy it at this time, right? Now it basically means you will not want to buy here. So you will not want to buy here, right? The reason is because if you buy at this point of time, then you have to pay some carrying cost. So a better choice for you is if you will use canola at this time, then you should buy it at this later time. So this basically means that you won't want to store canola for a long time, right? So it's really because of economic reasons. There's no need for you to pay this storage cost if you can get this canola in the future with the same price. So in this case, we can actually use a very simple discounted cash flow method. The idea is like this. So let's say we have 2 dates, okay? The initial date and date t. And on date t is the, so date t here is the maturity date. So on this, let's say on date 0, you will enter this contract. So you will enter the long position. Okay, you will enter the long position. And then on date t, the maturity date, you will have to pay F0, which is the futures price. And let's say the expected spot price on date t is given by EPT. Now what you can see here is essentially it says that on date t, you will pay F0 and you will get the expected spot price, right? However, if you think about time t and time 0, you can see that in the beginning, when you enter this long position, your cash flow is actually 0. So this implies that if you discount your future cash flows of F0 and EPT, then you should get a number of 0. Now, how do you discount F0? Well, you should use the risk-free rate to discount F0 because the futures price has been determined when you entered into this contract. So there is no uncertainty, right? So F0 is a fixed number. That's why you should use the risk-free rate to discount F0. And then this EPT, well, the futures spot price has some uncertainty, which means you should use a different discount factor, right? So let's say this discount factor is 1 plus K here. Generally, this is the required return on this commodity, and you could use capital asset price model to find out K. And then this discounted cash flow has to be 0. And if you manipulate this equation, you can find out the pricing formula like this. Okay, so let's look at this example here. So let's assume the TPO rate is 5%, the market risk premium is 8%, and the beta for orange juice is 0.117. Now let the expected spot price in 6 months be 1.45. Now what is the future price F0? So it's basically just about plugging numbers, right? So F0 equals expected spot price. So it's 1.45. And then the risk-free rate is 5%. So the key here is, how do you find out this K here, right? Well, as I said, you could find out K using CAPM. So K equals risk-free rate plus, do you have beta here? Oh, we have beta here. 0.117 times the market risk premium, which gives us a number of 5.94, right? So this K has to be 5.94. And then we also have this T here, that is number of years. And the maturity date is 6 months away. So we should use 0.5 here, which is like one half year. And then this gives us 1.444. Okay, that's perfect. So I spent like 60% of this semester's time on different assets, right? So we talk about 3 kinds of assets, right? We talk about equities. We talked about fixed income, more specifically bonds. And then we talked about derivatives, more specifically options and futures. I would say these are like basics of investment. Right? If you want to manage money, if you want to make some investments, then clearly you have to understand those different assets, right? You need to understand the things you want to invest in. Obviously, most of the time, people just buy equity. So understanding equity is like the basic requirement. But sometimes, or most of the cases, people will want to diversify. So in this case, a lot of people will choose some bond. So in this case, you need a good understanding of bond. And then sometimes people would go to more advanced investment, right? So in this case, they might want to use options or futures to make some bets or to do some speculation. Or you might want to use options or futures to hedge against some downside risk. Of course, these are more advanced methods, but I would say these things are quite useful, no matter whether you just want to invest in equity or you want to use fancier options or futures. So I hope these 3 chapters will be useful to you. Okay, so next we will move into more theoretical chapters. So first we will talk about risk, return, and performance evaluation. I think if you have taken corporate finance, then this part should be easy, right? Risk and returns. And this part, performance evaluation, is new, and it's actually quite useful because clearly if you're making your own investment, it's very important for you to understand what is your portfolio's performance, right? So you basically want to evaluate yourself. And if you want to invest in some mutual funds or ETFs, in this case, you will want to use the performance evaluation to evaluate those mutual funds. I mean, generally in the universe of mutual funds, you have a lot of choices. For Canada, I guess it should be over 5,000 different mutual funds. So, which one should you choose, right? Clearly, you can see that to answer this question, a very basic requirement is you need to understand how to evaluate its performance. So this is also a very useful chapter. This chapter is based on chapter 5, which is about risk and return. Chapter 24, which is about performance evaluation. Okay, so let's first talk about returns and risks. So first, we talk about interest rate. Now, there are basically two kinds of interest rates. The first one is called nominal. The second one is the real interest rate. If you have learned about, if you have taken macroeconomics, then you should have learned about these two different kinds of interest rates. So, nominal interest rate basically means the growth rate of your money. Real interest rate means the growth rate of your purchasing power. Right? So essentially, you can see that real interest rate is about purchasing power, and you can imagine that in real world, nominal interest rate and real interest rate should be different, right? For example, let's say you get 2% return from your savings account. However, you can see that if inflation rate is 2%, then your purchasing power will not change, right? So in this case, your nominal interest rate is like 2%, and your real interest rate is actually 0%. Now, how nominal rate and real interest rate are related? Well, think about this. Right. So let's say we start from nominal rate. Okay, let me see what's the notation here. So let's say the nominal rate is R known. And then the real interest rate is R real. And let's say I refers to the inflation rate. So let's say you have $1, right? And after 1 year, this will become 1 plus the nominal interest rate. But you can see that you get this amount of money because two things. The first is inflation. And the second thing is the increase in your purchasing power. That is the real interest rate. And these two things should be the same, right? So we will have 1 plus nominal rate equals 1 plus real interest rate times 1 plus inflation rate. So you can see that this is like a decomposition. That is, I decompose the nominal rate into two components, right? The first component is the real interest rate. The second component is the inflation rate. Now, if you do some mathematical manipulation, you can see that the left-hand side would become 1 plus I times real interest rate plus I plus real interest rate. Okay, my Apple Pen does not work. Okay, great. And you can see that this and you can see that this 1 will just disappear. And we can find out the real interest rate equals the nominal interest rate minus I and 1 plus I. Right. So that's how you get this formula here. Now, one thing is you can see that generally, at least for developed countries, I is generally very small for the last 2 decades. It's generally below 2%, right? So this implies 1 plus I is roughly the same as 1, right? So we could remove this I here. And we could write approximately the real interest rate equals nominal rate minus inflation rate. Okay, now you can see that basically, right, the real interest rate and inflation rate will determine nominal rate. Now you might want to ask, what determines real interest rate, right? What determines this guy? Well, it is determined in market equilibrium, right? So it will basically determined by the supply of money and the demand of money. Right? So you can see that households, they actually supply money through their savings. Now, who demands money? Well, business, right? Business, they want to make, if they want to make investment, then they have to borrow money. So in this case, business demands money. If you draw out these supply demand curves, what you can see here is, so let's say this is called amount of money. Right? So amount of money. And then the vertical axis is really the price of money, but it's essentially real interest rate. So basically, real interest rate is like the price of money. And you can see that supply curve should look like this, right? It basically means if real interest rate is higher, then people are more willing to put savings into banks. Now, demand should be like this, right? Because if real interest rate is higher, then businesses will be less willing to borrow money to make investments. So we should get a curve like this. And then you can see that this will determine a equilibrium. So this will determine the real interest rate. Of course, in reality, we have some third parties, right? We have government, we have central bank. And central bank and government can both modify these supply curve and demand curve. So generally, central bank can use monetary policies to modify the money supply curve. So if the central bank wants to pursue a loose money policy or expansionary monetary policy, then the supply curve will actually move to the right. So this will generate a lower interest rate. And if the government wants to pursue a fiscal if the government wants to pursue a expansionary fiscal policy, then it will actually increase the demand curve, right? The demand will be here, right? Okay. Why do I have this here? Okay, yeah. So in real life, right, we pay taxes. So basically, your your after-tax real interest rate will definitely get affected by tax rate. Right? So let's see how this is calculated, how the after-tax real interest rate is calculated. So let's say, again, the R norm refers to the nominal interest rate, and R real refers to the real interest rate, and I is the inflation rate, and T is the tax rate. So your after-tax real interest rate is your after-tax nominal rate, right? So it's R norm times 1 minus tax rate. And then we have learned real interest rate equals nominal rate minus inflation rate. So if you want to find out your after-tax real interest rate, then it equals after-tax nominal rate minus I, inflation rate. And then we could use some mathematical manipulation, and in the end, you can find the after-tax real interest rate equals the real interest rate times 1 minus tax rate times minus I times T. Now, what's interesting about this this formula is you can see that because tax is imposed on nominal rate, taxpayers will actually suffer from higher inflation rate. You can see here is as I increases, this after-tax real rate decreases, right? So it basically means that if real rate stays the same, the after-tax real rate suffers if inflation increases. Okay, now let's talk about calculating returns. So to be more specific, we will talk about how to annualize returns. So first, we start from the simplest case of calculating returns. That is, holding period return or total return from your investment. So let's say you're buying a bond with a par value of $100. Right? So let's say this is a zero coupon bond. So basically you can see that at time t, that is on the day when the bond matures, you will get $100. And let's say you paid $t at the beginning of your investment. So clearly to calculate your holding period return or total return of your investment, then you can see that it's basically 100 divided by pt minus 1. Right? So this is like very trivial. So let's say now we have three cases. Let's say we have half-year investment horizon, 1 year investment horizon, and 25 years investment horizon. So let's say we have these three different prices, right? So 97, 95, and 23. And then to calculate the holding period return, we will just use this formula. So what you can see here is we get returns here, and then we convert the return into percentage returns. So basically you can see that across these three different investments, we have very different numbers, right? For this 6-month investment, the total return is 2.71%. And for this 1 year investment, then the total return is 4.69%. And for this very long 25-year investment, the total return is 329%. So you can see that because we have different investment horizons, or because we have different time scales, it's actually hard for us to compare returns, because you can see that you get very different numbers. So basically we wanted to compare return with the same time scale. So that's why we want to annualize these returns. Right? And to annualize returns, we will use the effective annual rate. It's essentially annualized return. And the formula is pretty simple. It's just the 1 plus holding period return times 1 divided by t. Here the t refers to the number of years. So you can see that, I do have the example here. So if you look at the first case, right, this half-year investment, then you can see that EAR equals 1 plus R times 1 divided by T minus 1. So in this case, you can see that your 6-month return is this. Right? So it's 1 plus 2.71%. And you have 6 months, which means 2 periods. So it's 1 divided by 0.5 minus 1. So this gives us 5.49. And then the 25-year investment, the annual return is 1 plus R, 1 divided by T minus 1. So we have 1 plus 3 to 9%, and T should be 25. So this gives us 6%. So you can see that annualizing return is useful because you now can compare return, use the same 1-year investment horizon, right? Because we're talking about annualized return here. Okay, another way to think about annual return is the annual percent rate, or APR. And you can see that this is a number used by banks, right? If you look at your credit card statement, then generally bank will tell you your APR is like, for example, 22% per year, right? So what is APR? Well, APR is essentially the rate which is calculated as a simple interest rate. So APR is generally used for short-term investment. That is, investment with a time horizon smaller than 1 year. And in this case, you annualize the return using simple interest. If you look at EAR here, right? If you look at this guy here, you're actually annualizing the return using compound interest rate, right? So what you're doing is you would invest for the first 6 months, and you will continue invest for another 6 months. So this is compound interest rate. And if you're annualizing returns using simple interest rate, then what you will do is you will just use 0.271 times 2, right? So in this case, this number, 0.242, is APR, right? In terms of formula, it's easy to see this will hold, because this is exactly the definition of APR, right? So for example, if T is 0.2, then APR is essentially 2 times RFT, right? So basically, as I said, this is simple interest rate, right? You will just you will just use the first 6 month return, and then you will add the second 6 month return. This gives you APR. And you can see that if T is more than 1 year, right? Let's say T is 10, right? Then it's essentially the total return you get from 10 year divided by 10, right? Okay, because we know this hold. Because we know this hold. And then we could plug in RF by the definition of EAR. By the definition of effective annual rate, we can see that the total return equals 1 plus EAR and exponential t minus 1. Right? So we could plug in this formula. Right? So this essentially tells us how APR and EAR are related. Right? Of course, if you manipulate this formula, you will get the next one. That is how to get EAR given APR. Now, let's talk about a quirky way of compounding. That is, what is the limit of this guy? This guy. What is the limit of this guy here? So here I'm referring the word limit. What I'm trying to say is if I make t approaches 0, right? So in this case, you can see that if t approaches 0, it means that I am looking at a very small period, right? So let's say if t is 0.01, then you can imagine that this is about how many days? This is about 6.5 days, right? So now I am looking at a very small interval. And I am thinking if t approaches 0, it goes to the limit. How this formula will actually look like? Well, if you have some math background, you can actually calculate this limit. But now I will just give you the answer. So as t approaches 0, now we will have this continuous compounding. Essentially, as t approaches 0, the per period interval is very small. So you will continuously compounding your returns. And in this case, the EAR and the APR will be related like this. So this is the, so what's the name for this? I think it's called, so it's a mathematical constant. It's called Euler's number. So it's about 2.7, right? So this is how these two guys are related. So here, RCC refers to APR with continuous compounding. And of course, given this formula, we could find out if you have effective annual rate. Now, what is the APR under continuous compounding? Okay, now let's see this example. So here we have both EAR and APR, and both of these two guys are equal to 0.058. And you can see that clearly we could transfer from EAR to APR using the formula we just discussed. And we could also see that we could go from APR to effective annual rate. Again, it's just about plugging numbers. And you can see that we have different T here, right? So we have 1 year, 6 months to 1 day. And if we do continuous compounding, that is, as T becomes smaller and smaller as T approaches 0, then the APR is given by this formula. I won't talk too much about this because it's essential about using the formula. Okay, maybe one comment on this. If you look at this APR here, so the APR is fixed at 0.058. And then if you look at these numbers are effective annual rate, right? So what you can see here is as you compound more, these numbers actually increase, right? And you can see that this result is quite easy to understand, right? Because you can see that if you fix your APR and if you have shorter t here, if you have smaller t here, this means you will compound more. And we know that compounding is a very powerful force. And in the end, as you compound more, your effective annual rate should increase. Okay, finally, we could talk about some more about return and risk. So now let's talk about return, variance, and standard deviation. So first, we talk about expected return. Here, you're given a probability distribution, right? So basically, you can see that the expected return is given by the return under a certain state times the probability of a certain state. And then you will sum up all these numbers. So basically, you can see that, let's say, if your return is 0.1, if it's a good state, and then your return is minus 0.2 if it's a bad state. And let's say the probability of good is 0.8, probability of bad is 0.2. So you can see that these are RS and these are PS. And then the expected return is essentially 0.1 times 0.8 plus 0.2 times minus 0.2 times 0.2, right? Okay, variance. Well, variance is defined as the deviation between return and expected return squared. And then you will weight this squared deviation using probabilities. And then standard deviation is defined as the square root of variance. You can see that I go through the definition quite because for level course, you're supposed to know expected return, variance, and standard deviation. Okay, now let's talk about realized returns. You can see that if you're talking about probabilities, right? If you're talking about probabilities, you can see that you're given a probability distribution of returns. But in reality, you generally don't get this distribution. In reality, you will deal with realized returns. That is, if you look at, let's say if you go to Yahoo Finance, right? If you input Apple, right? Then you will find out Apple's returns, let's say over the past 10 years. So a basic approach to understand Apple's return is you will use these realized returns and calculate its average and its sample variance, sample standard deviation. Right? So that's like the basic entry point to understand Apple's shares. Okay, so first, what is a realized return? Well, it's pretty simple, right? If you have a investment, let's say you invest in Apple stock. Let's say you purchased Apple share at $100, and then at the end of the investment horizon, you have, let's say, the share price increased to 150, and let's assume you will also get a dividend of $3. Now the realized return is essentially 150 plus the dividend minus the initial price divided by the initial price, right? So I guess it's 53%. Now, after getting these realized returns, you can calculate average return. Well, we're talking about average return. It's like the simplest return you can calculate, right? So if you have 0.1, 0.2, 0.3, then average return is just the sum of these three guys divided by 3. So this gives you 0.2. So average return will give you a unbiased estimate of the expected return. And next, we could talk about geometric average. Geometric average is just really a fancy way to talk about annual return. So you can see how it works like this. Let's say you invest for number of n years. Right? And then you can see that, let's say in the beginning, you invest $1. So you can see that at the end of the year, your dollar value of your investment is 1 plus R1. And then you would continue to invest. So it's 1 plus R2. Right? And until the nth year, it's 1 plus Rn. And this is the total amount of, so this is the total amount of your money from investing in n years. And now we want to find out the geometric average return. As I said, this is really just about finding out the annual return. Right? So let's say the annual return is G, and you have invest for n years. So if annual return is G, then you have to put a exponential of n here, right? So this basically means G equals this guy, right? And you can see that geometric average return will give you the annualized return, and it gives you the basic measurement of your investment performance. Okay, next, sample variance and standard deviation. This really is like a statistics course. So sample variance is defined by this. T is basically the number of periods. And sample standard deviation is defined as the square root of sample variance. And you can see that it's quite easy to calculate the sample variance, right? So what you're doing is you're just look for the squared deviation from the average return, and then you will add up these squared deviations, and then you will divide number of periods minus 1. Okay, great. Now, Sharpe ratio. So after finding out the average return, we could find out Sharpe ratio. Sharpe ratio is defined by average excess return divided by standard deviation of excess return. Well, what is excess return? Well, it's the so excess return is return minus a benchmark return. And generally, people would use the risk-free rate as the benchmark return. Okay. So you can see that if you want to find out Apple's Sharpe ratio, you will look for Apple's average excess return, and you will calculate the standard deviation of Apple's excess return. Then you will look for the ratio of these two numbers. This will give you the Sharpe ratio. Intuitively, you can see that Sharpe ratio is a performance measure. It basically measures reward to risk ratio. So return is your reward from your investment, and standard deviation, which is a very classic risk measure, measures your risk. So you can see that if your investment has a larger Sharpe ratio, then your investment has higher performance. Okay. Now let's see this very simple calculation example here. Let's assume Apple has a realized return for the past 3 years, 20%, 20% minus 10%. And what is the average return, sample variance, sample standard deviation, and Sharpe ratio? Okay, now let's do the calculation. So we have three numbers. Average return. Well, this is easy. It's 20% plus 20% minus 10% divided by 3, which is it 10%? Yes, it is 10%. Now let's look for sample variance. Right, so sample variance is 1 divided by 3 minus 1. And we will add up these squared deviations. So the first guy would be 0.2 minus 0.1 squared plus 0.2 minus 0.1 squared plus minus 0.1 minus 0.1 squared. So you can see that this is the first return 20%, second return 20%, third return minus 10%. This 0.1 is just the average return. So we will get a number. Right? I don't know what's the number here. Let's say this is a number. And then sample standard deviation is just the square root of this number. Right? And then Sharpe ratio. Sharpe ratio is the excess return. What is the excess return here? It's the average return minus 2% divided by standard deviation, which is this guy here. Right? Of course, you have to figure out what is this number here. Okay, great. Now let's talk about more advanced risk measures. As I said, standard deviation is like the most basic classical form of measuring risk. Right? So generally, if a investment has a larger standard deviation, then we would say that this investment has higher risk. And I think for corporate finance, we always use standard deviation as a risk measure, unless we are specifically talking about risk management. But most of the time, we just use SD, this standard deviation, as risk measure. So why do we do this? Well, the reason is because traditionally, we assume returns follow normal distribution. Again, we are talking about statistics here. So you have to understand what is a normal distribution. So now you're seeing a picture here. So this is the probability density function. So this is the PDF, probability density function of a normal distribution. And the probability density function of a normal distribution is given by 1 divided by standard deviation, 2 pi e 1 over 2. I think it's x minus the mean divided by standard deviation squared. So here, sigma is the standard deviation, mu is the average or the mean here. And then if you draw out this function, right, you will find out the PDF of normal distribution looks like this. So it's this famous bell-shaped. And you can also see that we have some sort of probabilities marked on this picture. Right? So what does this number mean here? Well, it means that the probability of return which lies between 1 standard deviation is 68.26%. That is, the probability of return lies between 1 standard deviation is 68.26%. And then by the same reasoning, you can see that the probability of the return lying between 2 standard deviation is 95.44%, right? So in investment, we generally call this return as 1 sigma return. And you can see why, right? Because here sigma refers to the standard deviation. So this is essentially the -1 standard deviation return. And this is the 2 sigma return. And this is the 3 sigma return. Okay. Now let's see this example here. Suppose the annual rate of return on the SPTSX composite index is normally distributed. And let's say we assume this normal distribution has a mean of 10% and a standard deviation of 20%. Now, what is the probability that the return on the index in any year will be smaller than -50%? So if you draw out the bell-shaped curve, then you would know that its mean, which is the center of this curve, should be 10%. And then you will have this -1 sigma return, which is, okay, I'll use 1 sigma. So it should be 10 minus 20%, right? So it's minus 10%. So 2 sigma return is 10% minus 2 times 20%. So it's minus 30. And then 3 sigma return should be 10 minus 3 times 20%. So it's minus 50%. So what you can see here is we are essentially looking at this guy here, right? And we know that probability, right? We know that probability of the return lies between 3 sigma should be, okay, let me write a better sigma here. What a failure. So 3 sigma, because the sigma really looks like 6. And we know that this guy equals 99.74%, right? And you can see that what you can see here is this bell-shaped curve is symmetric, right? So this basically means P are smaller than 3 sigma should be 1 minus 99.3% divided by 2, right? Okay, let me make it easier to understand by, okay, so you can see that this shaded area, right? If you look at this shaded area, then the probability for this shaded area is what? Well, it's 99.7%. Then you can see that for this area, right? For these two pieces, their total probability should be 1 minus 99.34%. However, you can see that this guy and this guy, they should have the same probability. So if you want to find out the probability of the left tail, then you should divide 1 minus 99.34% by 2. Right? So again, you can calculate this number by yourself. Oh gosh. Okay. Okay, now, why do we want to assume returns have a normal distribution? Well, the reason is because it's easy. Because normal distribution makes our life so much easier. The textbook gives you 4 valid reasons, and I think those are good reasons. So the first is normal distribution is symmetric. Why it is symmetric? Well, look at this nice picture. It is symmetric, right? And why do we prefer symmetry? Well, because if distribution is symmetric, then standard deviation is a complete measure of risk. At this time or now, this first reason is actually ambiguous, because you might not know why standard deviation is a complete measure of risk. You will see this in the near future. So let's just first state the first reason here. And now let's move on to the second reason. So the second reason is portfolio return is normally distributed if investments in this portfolio have normal returns. So it basically means something like this. Let's say you have a portfolio and you have 60% invest in Apple, and you have 40% invest in Microsoft, and your portfolio return would be 60% times Apple's return plus 40% times Microsoft return. And if Apple return is normal, if Microsoft return is normal. Then the portfolio's return will be normally distributed. Right? Now the second reason is scenario analysis is much simpler. The reason is because if we want to define normal distribution, we only need two parameters, right? We only need mu and sigma. That is, to define normal distribution, we only need mean and standard deviation. So you can see that whenever you want to use normal distribution to model investment returns, you only need to deal with two parameters. So this is really simple because some other distributions have more than two parameters. And if you use a more complicated distribution, you can imagine that your modeling process will be more complicated. And then the fourth reason is when constructing portfolios of securities, the dependence between securities can be summarized by a single correlation coefficient. So this basically says when you're constructing a portfolio, let's say you have multiple investments, right? Apple, Microsoft, let's say Lululemon, let's say Peloton, right? If you want to correctly understand your portfolio's risk and returns, then at the basic level, you have to understand how these four different stocks are related. Now, if these four stocks, their returns satisfy normal distribution, then you will only need correlation to understand these different stocks relationship. So again, this really simplifies your life. However, the reality is messy. And if you look at data, security returns do not satisfy normality. They're not normally distributed. So what's the implication of this? Well, it basically means that if it is not normally distributed, then now standard deviation is not a complete measure of risk. And we know that Sharpe ratio is defined by the ratio of return and standard deviation. So if standard deviation is not a complete measure of risk, this implies that Sharpe ratio is not a complete measurement of performance. So why returns are not normally distributed? Well, if you look at data, then you can see that generally security returns feature asymmetry and fat tail. Oh boy, it does not work. Okay, so let me give you some overview of the asymmetry at fat tail. We will talk about these two deviations in the next class in more details. Okay, so what is asymmetry? Now, this is normal.
Here's some information.
Oh gosh. So this is normal. So this is a normal distribution, right? So it is quite asymmetric. But if you look at data, security returns actually look like this, right? So this is called left skewed. And you can see that it is asymmetric, right? It has a longer tail with negative returns. And security returns also feature fat tail. So what is fat tail? Let's say this is let's say this is normal distribution, right? So fat tail means if you look at data, it will look something like this. So you can see that the fat, sorry, not, now you can see that the tail here is fatter, right? Because you can see that the thickness of tail of the normal distribution is given by this. But for security returns, its tail looks like this. So it's a fat tail distribution. Now, why does this matter? Well, the reason is because if the tail is fat, you can see that if the tail is fat, it basically means there is a larger probability you will suffer from negative returns, right? Compared with a normally distributed return, right? Okay, so that's for today's class. We will talk about these interesting deviations in the next class in more details.